Hi all, we are going through chapter 9 now. So chemical bonding, basic concepts of bonding now. So how two atoms might bond to one another to form a molecule or a compound. So to get started with chapter 9, we're going to go into this topic of counting bonding and non-bonding electron pairs in Lewis dot structures. We'll practice drawing these on our own. We're just going to start getting used to looking at Lewis dot structures first. So within Lewis dot structures, we may see ionic bonding and covalent bonding. So ionic bonding, like we've seen, these are actually not real bonds. They're just electrostatic interactions between a cation and an anion. So this ionic bond, in quotes, the electrostatic force that holds ions together in an ionic compound. For an ionic compound, we know we have our cation that will be positively charged, along with the anion that's negatively charged. There's not a true bond between them, but there's an electrostatic attraction between the two charges. So what ends up happening when this cation is formed and this anion is formed is we know cations will lose electrons to become positively charged, whereas anions will gain electrons to become negatively charged. For example, then lithium is 1s2, 2s1. It's going to give up one of these electrons to fluorine. It's going to give up this one electron to then become positively charged. So it's a cation. It lost an electron to become positively charged. Then fluorine is 1s2, 2s2, 2p5. Fluorine will gain that electron from lithium to then have a full complete octet, so 2p6 over here for fluorine. And technically this is fluoride now because it's the negative form, it's the anion form, so we change that ending to IDE. Then this 1s2 represents what's left over for lithium. When it gave up this one electron to fluorine, all that's left for lithium as a cation is just 1s2. So lithium would normally have 3 electrons, so we see here 2 electrons and a third. When it gives up that one electron to fluorine for fluorine to become fluoride, all that's left is 2 electrons in the 1s2 orbital. Then again, fluorine wants to gain an electron, so it has a complete octet. So 1s2, 2s2, 2p6 now, because it transferred that electron. That electron was transferred from lithium to fluorine. So this works out for both of them because fluorine then has a full complete octet. Remember, octet is having 8 electrons in the outermost shell. So we're looking for the highest value for n to call that the outermost shell. So 2 electrons plus 6. Now fluorine has a complete octet. So again, for an octet, there's 8 electrons in the outermost shell, where we define shell as the value for n. So the outermost shell is going to be the highest values for n we see within an atom's electron configuration. The octet describing the outermost shell, we no longer look at this lower value for n, where n is equal to 1. We're just looking at the two n equal 2 to see 8 electrons total to form a happy complete octet. Why is lithium happy then when it gives up this one electron? Well, then lithium actually gets to fill its duet. It's happy with just 2 electrons here in 1s2, so it's happy with a full duet, whereas fluorine is then happy with a complete octet. So to start looking at these different structures, we can see, so we have this atom here in the middle. We see just 1 electron around lithium. This 1 electron is represented by a dot here. This is the valence electron. So as we're seeing, we're not showing these 1s2 electrons, just the 1 valence electron around lithium. When it gives up that valence electron, it becomes positively charged. It still has 2 electrons in the 1s subshell, but in these sorts of depictions, we don't show the inner shell electrons. We're only going to see the valence electrons that are in the outer shell. So 1 electron gets removed from lithium to form a cation. Here's that 1 electron that can then get transferred to fluorine. Fluorine itself has more than just 7 electrons, but fluorine has 7 valence electrons. So when we're drawing this sort of depiction for fluorine, we're going to draw 1, 2, 3, 4, 5, 6, 7 valence electrons. We're not showing the 1s2 electrons. We're not showing the 1s2 electrons because those are the inner shell electrons. So for fluorine, this is 1s2, then this is 2s2. So 2s2, then we go over to the p block, and we're still in the 2 row. So n equal 2 row, 2p, 1, 2, 3, 4, 5. Fluorine has 7 valence electrons because we define those valence electrons as the electrons that are in the outermost shell. The outermost shell for fluorine is not n equal 1, it's n equal 2. In the outermost shell of n equal 2, we have 2 electrons here and 5 here. That's 7 valence electrons for fluorine. So just again, we don't show these inner shell electrons in showing depictions like this. We're only showing the valence electrons, where the valence electrons are the outer shell electrons. And again, shell is the n value, so n equal 2 is the outer shell compared to n equal 1 here. So here's fluorine depicted. It has 9 electrons, but we're only showing the valence electrons in a depiction like this. It can gain an electron from lithium that gave up that electron. When fluorine accepts that electron, it then forms this conformation. It now has 8 valence electrons around it, so now fluorine is happy. When it gained that additional electron, so this one, it gained an additional electron, so something like here, then it becomes F minus. Lithium lost an electron to become lithium plus. This is technically the Lewis dot structure for lithium fluoride. We show the charge here on lithium, then we show those 8 valence electrons around fluorine, causing it to then have a -1 charge because it's an anion. It gained an additional electron. So aside from ionic bonds, we can have covalent bonds. Covalent bonds are true actual bonds. It's a chemical bond in which 2 or more electrons are actually shared by 2 atoms. Ionic bonds aren't really sharing electrons, they're more of a transfer of electrons between one atom that will become a cation and one atom that will become an anion. So more of a transfer of electrons for ionic bonds. And they're not really true bonds. They're these electrostatic attractions or electrostatic forces. Covalent bonds, however, are actually true bonds. The electrons are not transferred, but they're shared between 2 atoms. So why should 2 atoms share electrons? Well, still their ultimate goal is to reach a happy octet. For example, our Brinkelhoffs. Fluorine is one of our Brinkelhoffs. That means it exists as a diatomic like F2. Cl2, N2, I2, those are also all Brinkelhoffs. F2 is a diatomic, and between the 2 F atoms, they actually share a pair of electrons. So we just looked at fluorine having 7 valence electrons on its own, and to draw in those electrons, we'll draw 1, 2, 3, 4, 5, 6, 7. We have 2 of these fluorine atoms just like this. So 1, 2, 3, 4, 5, 6, 7. For this fluorine atom to reach a full happy octet and this fluorine atom to reach a full happy octet, they're going to share these electrons so that this fluorine then has a happy octet because it's sharing this one from this atom, and same for this atom. So 7 valence electrons and 7 valence electrons, if they share those 2 electrons here between them, they'll both have a happy complete octet. And we didn't have to bring an electron in from somewhere else. We didn't have to add any electrons. They just already exist with 7 valence electrons. And so they share those two to reach a happy octet. And just as a reminder again, how we know that fluorine has 7 valence electrons is because we go from left to right. 1 valence electrons, 2 valence electrons, 3, 4, 5, 6, 7. Then our noble gases technically have 8 valence electrons, or for helium, just 2 valence electrons. So 7 valence electrons is really close to having an octet. So if it shares that 1 electron with another fluorine atom, they'll both have a happy octet. So something we'll see soon is that fluorine F2 can be represented like this, so 2 fluorine atoms sharing that pair of electrons. It turns out that that sharing of electrons is equivalent to a bond, a covalent bond between those 2 atoms. So this is a single covalent bond between the 2 atoms. Within that bond is really just the 2 electrons that the 2 fluorine atoms are sharing between themselves. So here's that pair of electrons that are being shared. That is the covalent bond. So these are the same thing, but typically we see it represented like this as an actual bond between them. Rather than showing these 2 electrons just listed like this here between the 2 F atoms, again, we typically show it as a bond. And again, it's a covalent bond and not an ionic bond because it is a true sharing of electrons. Then these are considered lone pairs of electrons because either the electrons are in a bond or they're lone pairs. So we can have electrons in a bond, it's 2 electrons in a bond, or we have lone pairs of electrons that are just around the atom that are not participating in a bond. So we've talked about water a decent amount in the past, and for hydrogens, they both have 1 valence electron apiece. How many valence electrons does oxygen have? Well, based on its placement in the periodic table, oxygen has 6 valence electrons. So here's 1, 2, 3, 4, 5, 6 valence electrons for oxygen. The reason water is a stable molecule is because hydrogen wants to fill its duet, oxygen wants to fill its octet, so hydrogen filling its duet is sharing 1 of these electrons with oxygen. Then oxygen benefits as well because it shares that electron from hydrogen. So this happens on both sides of oxygen, where oxygen ends up with a happy octet here in the middle. Then hydrogens end up with a happy duet here on the sides. So remember, within each covalent bond, that's really 2 electrons that are being shared between this atom and this atom. 1 electron being shared came from hydrogen. The other electron being shared came from oxygen. So we see that again on both sides of the oxygen to form water, which is H2O. And so it turns out within covalent bonds, we know this is a single bond, this is a single bond. Each of the single bonds holds 2 electrons within that bond. We do have cases where we can see double and triple covalent bonds. For a double bond, this is a sharing of 4 electrons here in total per set of double bonds. So 4 electrons shared here, 4 shared here. So between this oxygen and carbon, that's 4 shared electrons. Between this carbon and this oxygen, that's another 4 shared electrons. The reason we see this for carbon dioxide is, again, because both atoms, or all 3 atoms, want to reach a happy complete octet. The best structure that allows oxygen and carbon and this other oxygen to have a happy complete octet is for this to have 2 bonds between them. How does carbon have a happy complete octet? Well, here's 1, 2, 3, 4 electrons, 5, 6, 7, 8. Carbon is happy with a complete octet. with two double bonds, 4 double bonds total, and no lone pairs of electrons on the carbon. So here in this structure, carbon has 4 bonds around it and no lone pairs. It turns out for both oxygens, they'll also have the double bond, but that's just 4 electrons here. So for each oxygen, that's 2 bonds and 2 lone pairs. 2 lone pairs, a pair meaning 2 electrons, so 2 lone pairs of electrons and 2 bonds from each oxygen. And there are 2 oxygens here total in this molecule of carbon dioxide, or in this compound, I can say, of carbon dioxide. Compounds have 2 or more unique elements, molecules do not. So something that is a molecule would be Br2 or F2. Because these are not unique elements, they're both bromine or both fluorine. So single covalent bonds, double covalent bonds, we just call double bonds. We can also have triple bonds as well. In a triple bond, that is now 6 electrons shared between the 2 atoms. So 1, 2, 3, 4, 5, 6, where each pair is a bond. So one bond contains 2 electrons, or in other words, it contains a pair of electrons. For nitrogen, it has 5 valence electrons. 1, 2, 3, 4, 5. For nitrogen to have a full complete octet when bonded to another nitrogen, remember nitrogen is one of our Brinkelhoffs. For N2 to be the most stable, for this nitrogen to have a happy complete octet, as well as the other nitrogen here, we need to have a triple bond between those 2 atoms. How does that work that they have a happy complete octet then? Well, this is 2, then 3, 4, 5, 6, 7, 8. So this is 8 valence electrons around nitrogen after it's sharing a triple bond with this other nitrogen. So nitrogen starts out with 5 valence electrons. To have a happy complete octet, it needs to sort of share 3 electrons with another nitrogen. To share 3 electrons means that it's sharing 1, 2, 3 electrons with this other nitrogen so that this has a happy octet and this one has a happy octet. And so again, that octet is 1, 2, then 3, 4, 5, 6, 7, 8. It's sharing 3 electrons with the other nitrogen, so it's not contributing all 8 electrons from itself. It's forming bonds to then be able to share those electrons to have a happy octet. So then in this conformation with a triple bond between the 2 nitrogen atoms, they both have happy complete octets. They're both surrounded by 8 electrons now in total. So for each nitrogen here, it's participating in 3 bonds, right? 1, 2, 3, and 1 lone pair of electrons. So 3 bonds, 1 lone pair of electrons. That's ionic bonds versus covalent bonds. For covalent bonds, we can have single, double, and triple bonds. And so the lengths of these covalent bonds, a single bond is longer than a double bond, which is longer than a triple bond. Even just comparing to single bonds, we can see a difference in this length here of that single bond. So H2 is going to look like this, HI. Well, iodine has 7 valence electrons. So it's contributing 1, 2, 3, 4, 5, 6, and then 7. Then when it forms a covalent bond with hydrogen, it now has 8 valence electrons around it. It has a happy octet. Hydrogen contributed 1 electron to iodine. Then for hydrogen to have a happy complete duet, it had 1 electron it contributed. Then it's sharing this electron that's coming from iodine. So happy octet, happy duet in this bond. The single bond here between two H's is shorter than the single bond here between hydrogen and iodine. For instance, for the carbon-hydrogen single bond, that's about 107 picometers, carbon-oxygen single bond, about 143 picometers. So when looking at the same two atoms, for the same two atoms, for example, we can look at carbon-oxygen double bond is 121 picometers, whereas the carbon-oxygen single bond is 143 picometers. But a pattern to be aware of when looking at a bond between the same two atoms, like C and O both times, the single bond is the longest, the double bond is shorter, and then a triple bond would be the shortest of the three types of bonds when just comparing that within the same two atoms. We're just looking at that within a bond between the same two atoms. A good example to look at this then, since carbon and oxygen don't typically form triple bonds, but carbon-nitrogen 143, carbon-nitrogen double bond a little bit shorter, carbon-nitrogen triple bond even a little bit shorter. So longest next, and then shortest, longest for the single bond, shortest for the triple bond. And so here's this table 9.3 that just compares an ionic compound to a covalent compound. So carbon tetrachloride, that has covalent bonds between the chloride and the carbon. Again, we'll practice drawing a lot more Lewis dot structures here in chapter 9. We're just kind of getting familiar with the types of Lewis dot structures and what we might see as far as bonds between two atoms. Interestingly, even though ionic bonds aren't really true bonds, they're these electrostatic forces or attractions between oppositely charged atoms. Even though they're not true bonds, they have really high melting points compared to covalent molecules or molecules that contain covalent bonds. These compounds with ionic attractions also then have really high boiling points, even compared to a molecule that has covalent bonds. So while this isn't a true bond, ionic interactions are really, really strong. Ionic attractions are really, really strong. You'd have to heat up this compound a whole lot to see it actually boil. So over 1,400 degrees C is where we'd see sodium chloride actually start to boil. So that's a really, really high temperature. So given that background on covalent and ionic bonds, let's do this practice problem before we start to draw Lewis dot structures. So here we have the Lewis structure for HF, or hydrogen fluoride. This is a molecular compound, right? Because it contains two nonmetals. We name the cation first, or hydrogen, then the anion, and we change that ending to IDE. Here we want to count the number of bonding pairs and the number of lone pairs around the fluorine atom specifically. So as we'll do, we will be chemists and use Lewis dot structures to show how the valence electrons in a molecule or polyatomic ion are arranged. By looking at a Lewis structure, a chemist can tell at a glance which electrons are bonding electrons and which ones are not. Our two distinctions are going to be bonding electrons and versus lone pairs of electrons. Lone pairs of electrons do not participate in a bond. Because the bonding electrons and non-bonding electrons, so lone pairs are the non-bonding electrons. Because these are almost always paired up, we rarely will see just a single electron like this. Those electrons usually come in pairs. So that's what we call it, a bonding pair or a non-bonding pair. So a pair of two electrons. So the highlighted electrons around the fluorine atom are forming chemical bonds. This highlighted pair is participating in a bond between hydrogen and fluorine. We can tell that each pair of electrons are bonding pairs because they're drawn right between two atoms. That means they are being shared by the two atoms to either reach a complete duet or a complete octet. So in this case, between HF, this is one bonding pair between H and F. If we're going to draw this like a true covalent bond, we would see the molecule drawn like this. This is a covalent bond. This contains two electrons. These are the bonding pair of two electrons. So drawing it like this is the same thing as drawing it like this. We'll start to eventually draw it mostly like this to show it as a true bond, even though we know this bond does actually contain a pair of electrons between those two atoms. So those were the bonding pair of electrons. We also have non-bonding pairs of electrons, or also known as lone pairs of electrons. They're lone pairs, they're non-bonding. They're lone pairs, non-bonding, they're not drawn directly in between two atoms. So these three lone pairs are just electrons around fluorine. They're not participating in a bond between hydrogen and fluorine. So here for HF, around just the fluorine atom, those are three lone pairs, three non-bonding pairs of electrons. So our final answer here, just looking at fluorine, there's one bonding pair. So one bonding pair and three lone pairs, which are our non-bonding pairs. Lone pairs, non-bonding, bonding pairs are what form those covalent bonds. And again, HF is a molecular compound, so we'll see true covalent bonds between the atoms versus ionic compounds. If a compound is an ionic compound, that has ionic bonds, remember that's in quotes, or ionic interactions between atoms. Whereas molecular compounds will contain covalent bonds between the atoms. So ionic versus covalent bonds, bonding pairs versus lone pairs. Next, we're going to go into predicting the relative electronegativities of atoms.